let's just resume where we left off last time. So we looked at minerals, we're starting to look at rocks, and we covered this basic split into the three broad classes of rock that are encountered. And I'm just going to spend a few minutes going through each of those to describe sort of typical characteristics, origins, things like that. So, igneous rocks, those of you with Latin GCSE may have worked out that igneous probably is something to do with hot, fire, and so on. Come in two types. They can be intrusive or extrusive. And the difference is essentially whether or not the melt makes it out onto the surface of the earth or not. So intrusives are forced into the crust but don't make it out, and so they just solidify rather slowly in situ. And the way this works is, we talked about subduction zones and generation of melts in those processes. So the magma that arises it's more buoyant, and it's really quite corrosive, and it's hot, so it corrodes its way up towards the surface of the earth, and sometimes it makes it and sometimes it doesn't. And if it doesn't make it, then it just stops somewhere, and it will very slowly, over long periods of time, cool down and crystallize. So that gives you an intrusive igneous rock. If, on the other hand, the rising melt does make it all the way to the Earth's surface and comes out, then that's what we know as volcanism and volcanoes, and a characteristic of things like the mountain ranges at convergent plate boundaries, or else characteristic of divergent plate boundaries along mid-ocean ridges and such like. And so extrusive igneous rocks are really just solidified volcanic lavas. And when you look at the very substantial array of igneous rocks that nature confronts you with, then you want to try and rationalize them to some degree. And the place to start is using simple physical characteristics, such as the texture. So if you cool an intrusive rock maybe over tens of millions of years, because rock itself is actually a rubbish conductor of heat, so you've got a lot of heat in the magma and it's just very slowly dissipated. You think of your undergraduate lab experiments. If you crystallize something out and you crystallize it fast, you get tiny little crystals. If you crystallize it out slowly, you get bigger, chunkier crystals. And rocks are just the same. They're really simply a fractional crystallization experiment. And so the cooling rate is what dictates texture to a large degree. Extrusives cool fast because they're slapped onto the surface of the earth, and therefore they cool rapidly, and the crystals that comprise them are often small, sometimes to the point where actually they don't even crystallize discrete phases at all, but actually solidify as a glass. Intrusives, on the other hand, because they cool over a very long time, the crystals grow big and chunky, and you can see very clear differences in texture within an intrusive rock. And the composition, well, in the end, if you solidify the whole of the parent melt, the bulk composition of the rock that results must be the same as the starting melt. But you won't necessarily crystallize a single phase. So as you start to cool a melt, then you will reach the point where you exceed the solubility limit for some phase, and you will start to crystallize that phase out. And because that phase's composition is not representative necessarily of the bulk melt, then the composition of the melt that's left behind will therefore change. So, for example, if you precipitate quartz out of a melt, you're taking out silicon and oxygen and nothing else. Therefore, the melt that's left behind, if you're precipitating quartz, will become relatively depleted in silicon and to a degree oxygen, and enriched proportionately in other things that might be in there, like sodium, potassium, magnesium, aluminium. So what you effectively have is you have this complex sequence of fractional crystallization processes which go on. And that's why rocks are not, or igneous rocks are generally not monomineralic. They've got more than one mineral in, because as they've gone through their cooling history, the melt composition has changed, the thermodynamic stability of the phase with which the melt is saturated has changed, and therefore a different solid phase has crystallized out. And you can play all sorts of dreadfully complicated games with ternary and quaternary phase diagrams when you're looking at igneous petrology. So let's try and put some structure onto the classification of igneous rocks. So we're differentiating extrusives from intrusives. We've already met one of the other big discriminators, which is the silica content. And we met that back in our first lecture. And there's one group which is high in silica, more than 66% SiO2. There's another group which is a bit lower. There's another group lower again, and there's some quite unusual ones which are very low silica content melts. And names used to describe these different classes of rock are, you'll find acidic or felsic or silicic, intermediate's easy, mafic or basic or alkaline, and ultramafic or ultrabasic, used for the lowest silica rocks. And rock names, the extrusives, so high silica lavas, solidified, are things called rhyolites. Intermediates can be things like dacites, basalt, and andesites, and the low silica volcanic rocks are basalts. The intrusive equivalents are granites, granodiorite, diorite, gabbro, peridotite, dunite, have no extrusive equivalents. And the minerals within them are characteristically, in the silica-rich melts, the silica-rich minerals, including quartz itself. If you think back, quartz was the most inefficient way to use silica because you're not taking anything else out with it. So you only find that in the most silicon-rich melts. You get feldspars, you get amphiboles, the double-chain silicates, and biotite is a mica. By the time you're down to these lower intermediate silica contents, you've lost the free quartz, and these rocks will tend to be feldspars, amphiboles, pyroxenes, and micas, the sheet silicates. And the trend in mineralogy is consistent as you go to still lower silica contents. So you've got olivines, pyroxenes, and calcium feldspars more than the alkali feldspars in the basic rocks. And finally you get into some fairly weird rock mineralogies when you're down to these unusual rocks. And we've got some pictures of them. So they're arranged in the same order as that preceding table. So rhyolite is the high silica melt. It's pinkish in colour because it's dominated by feldspar and quartz. All fine-grained because it's cooled rapidly. So that's what it looks like. The equivalent is a granite, which we all know and love. And you can see the much coarser crystallinity in here. These sort of dirty milk bottle grey inclusions are actually crystallized quartz that's come out. Quartz in here is too small to see with the naked eye because it's crystallized so fast. Andesite and diorite again, so we're into intermediate rocks. So here we've got a feldspar amphibole pyroxene mix, and again broadly similar. This has got lumps of broken up other rock debris in it. The fine-grained matrix is the lower silicate melt. Basalt, lower again. This is a sort of fairly typical mid-ocean ridge basalt, lots of bubbles in it. And olivine crystallised out after initial solidification, so green crystals of olivine growing in some of the voids. Gabbro is the intrusive equivalent, and dunite is essentially a pure olivine rock, so it's dark in colour, massive, there you are. So don't really want you to worry about all the detail, but you can start to see patterns, finer crystallinity, coarser crystallinity, and consistent change in mineralogy as you go from high silica to low silica. Okay, sedimentary rocks, second group. A lot of rocks form, we've just been talking about intrusive and extrusive igneous rocks. Now they form in conditions where they're really not particularly happy. So, for example, if you crystallise out a granite, 30 kilometres down or something like that, the environment in which it crystallises is very different from the surface of the Earth. So if eventually over geological time that granite finds its way to the surface of the Earth through tectonic movements, erosion and so on, then suddenly those minerals, which were quite happy thermodynamically when they crystallised out, find themselves in very different conditions. There's the atmosphere, which is relatively aggressive. It's wet, and water is a very good solvent, and the temperature is lower, the pressure is lower. So the response of many of the minerals that make up rocks to finding themselves in these conditions is to undergo a series of alteration processes. Now, thermodynamics tells you where those minerals will alter to, but tell you nothing about how fast the mineral will go along the path towards alteration. And most minerals do not alter very fast at all. You put a lump of granite, we build buildings out of granite. Granite is not actually thermodynamically stable on the Earth's surface, but it's not so unstable that you can't build a building out of it and expect that building to remain standing for many, many, many decades. You don't see rapid alteration. We're talking very slow chemistry here. But nonetheless, it's a chemistry which goes on and can be accelerated by some of the physical processes which operate on the Earth's surface. And one of the things you find is that if you think about the granite, well, any of these, you've got different minerals all intergrown together in here. Now, their physical properties will be different. So, as you heat them up, as you cool them down, they may expand and contract to different amounts. And what that leads to is it leads to initially stresses around things like grain boundaries, and eventually to microfractures. So you start to destroy the physical integrity of the rock, and eventually it will start to crumble away, and then the debris that results gets moved around, and that forms, when you deposit it, squeeze it so it solidifies again, that becomes what's called a detrital sedimentary rock. So here are some examples. So a breccia is a sort of coarse-grained rock with angular fragments. A conglomerate is the equivalent, coarse-grained, but you've got much more rounded component fragments. Sandstone is self-explanatory. It's sand-sized particles. We'll look at the more detailed classification in a minute. Sandstone is... Actually, I'm slightly surprised we're here. Ah, yes, we're doing it this way around. Okay, so sandstone comprises sand compacted, cemented together to make a solid rock. Claystone is clay-sized particles which have undergone the same process. A marl is simply a calcareous clay or mudstone. Travertine is silicious deposit. Bauxite is a residual rock. So you leach a rock intensely, you leave some things behind. One of the things you tend to leave behind is hydrated aluminium oxide, which we call bauxite. So the first half dozen are detrital sediments. The last two have a slightly different origin we'll come to in a minute. Okay, and here we are, the last two. The alternative route to producing a sedimentary rock is not just to move debris around and make it back into a rock, but it's actually to do some chemistry. So the second class that you encounter are what we call chemical sediments. And the medium in which this sort of chemistry generally operates on the surface of the Earth is in water. And you can find that either you tweak your water chemistry to drive a precipitation reaction, or else you just keep taking off the solvent, and eventually, as you do in the inorganic lab or anything, you take off enough solvent, you'll start to crystallize out something. One of the commonest sedimentary rocks is limestone calcium carbonate. And that's very widespread because actually shallow ocean waters, which comprise a significant part of the Earth's surface, and at times in the past have comprised rather more, they're actually slightly oversaturated with respect to calcium carbonate. So it's actually very easy to trigger the precipitation of crystalline calcium carbonate onto the sea floor. And those deposits will just build up over time. Also, because calcium carbonate is biologically important, lots of things make their shells out of it, and their skeletons in some cases. So you will find that actually biological processes will tend to drive the precipitation of calcium carbonate. And when the organisms who've got a calcium carbonate shell die, the calcium carbonate shell sinks, and that helps to accumulate calcite as well. The alternative approach is what are called evaporite deposits, where you just take a brine, a seawater, and you just keep concentrating it. And there are a couple of examples today. The Dead Sea is one, the Great Salt Lake in Utah is another, Salton Sea in California is a third. And you just keep taking water out, and eventually you drive the crystallization of a sequence of minerals from relatively insoluble to really what you'd normally think of as being quite soluble. So gypsum is the first to come out, hydrated calcium sulfate. After a bit, you've got your water activity in your solution has fallen too much. You can't waste 2 molecules of water precipitating 1 molecule of calcium sulfate. And so you precipitate a different form of calcium sulfate, which is the anhydrous version, the mineral anhydrite. If you keep going again, you precipitate sodium chloride, and eventually, right at the end, you precipitate potassium chloride. And did any of you see that piece on the telly news a week or so ago about potassium deposits under the North York Moors? Yeah? No? Anyone take any interest in current affairs? No? Okay. At times in the geological history of the British Isles, we've been down here, so you find gypsum and anhydrite quite widely in the geological record. They're quarried, for example, down in Leicestershire. British plasterboard quarry them and make plasterboard, make building materials out of them. There's a lot of salt underneath Cheshire, but what's unusual is the Cheshire deposit is almost all sodium chloride. The intense evaporation when they were laid down is elsewhere. So you find the potassium derived from at the same time, for example in Stassfurt in Germany, but also underneath the North York Moors. So potassium chloride is relatively uncommon, relatively valuable, and there's a big debate about should we should we mine underneath the North York Moors National Park because we want to get at this potassium. And trust me, it was all over the telly news the other day. No, I shudder to think what you lot were watching on the telly instead. Right, to try and put some structure on the classification of sedimentary rocks, this is looking at detrital sediments, and the most important point is simply how big are the crystallites, the bits that make them up. And there are various different scales. This just happens to be one. But so basically you've got big lumps over here, tiny lumps over here, and depending on the size of your lump, you give it different names. But crudely, you can think of gravels as being coarse, sands as being finer, silts finer again, and clay the finest fragments. Then the next thing to think about is how well stuck together they are. Because if it's like a beach, then it's not really a rock at all. But as you compact it and cement the individual crystallites together, so a gravel will evolve into a thing called a conglomerate, a sand into a sandstone, a silt into a siltstone, a clay into a claystone. There's some logic to the naming of these things. And if you get mixed particle sizes across the silt clay size ranges, then that's sometimes referred to as a mudstone. And then within this, you have a number of other criteria used to differentiate. So, for example, I pointed out the conglomerate, which was the rounded large fragments. If the fragments are actually angular rather than rounded, then it's a rock type called a breccia. If you've got a sandstone with a whole bunch of feldspar in it, then that's a thing called an arkose. Or if you've got a rather messy, nasty one, particularly with some clay in it, that's a thing called a greywacke. And a clay size, if you're in the clay size range, but actually the evolution of the rock has encouraged it to fracture in a particular direction, which gives it this property called fissility, then a rock that has that characteristic is a thing called a shale. So again, don't get too stressed about the details. What I want you to take away from this is that there is some order to this classification, based primarily on size and subsequently on the extent to which the rock is stuck together. Within the chemical sediments, I've just picked a number of examples here. So we've talked a lot about limestone, which is calcium carbonate and comprises calcite, sometimes aragonite. Dolomite is to a degree related. It's double carbonate, calcium magnesium carbonate. Magically, the rock dolomite comprises the mineral dolomite. We have sedimentary iron formations, which turn out to be quite important when we try and understand the evolution of the Earth and the early atmosphere and stuff like that. So we'll actually come back to iron formations, sedimentary iron formations, in about 6 or 7 lectures' time. But you can find sedimentary iron deposits as silicates, oxides, or carbonates. Iron silicates, well, I haven't given you an iron silicate example. Hematite and limonite are 2 examples of iron oxides. Siderite is an iron carbonate. Evaporites we've talked about. You can get chemically precipitated silica. You can get chemically precipitated calcium phosphate, the mineral apatite. And then some people put coal, gas and oil as chemical precipitates as well, but that's a bit contrived. So those are the principal sedimentary rock types. And metamorphic rocks, if you want a hideously complex set of rocks, get into metamorphic petrology. There are two processes which give rise to metamorphism. And one is relatively localized, and that's a so-called contact metamorphism. We talked about an intrusive rock sort of sitting there, embedded in the Earth's crust, cooling down over tens of millions of years. And all of that heat has to be dissipated. And it's dissipated through what they call the country rock, the surrounding rock mass that already exists. And you don't, that doesn't have no effect on that rock. So by putting something hot relatively close to existing rocks, so you drive a whole sequence of chemical change, and that is reflected in mineralogical change. And, you know, statement of the bleeding obvious that the closer you are to your heat source, the more intense the alteration will be. So in an ideal situation, you have the heat source in the middle, and you have zones of alteration around it moving away. They're the so-called metamorphic aureole. So you've got a whole sequence of different degrees of alteration with different characteristic rock types and mineralogies. The other thing you can have is what they call regional metamorphism, where an existing rock gets caught up in these big tectonically driven processes and gets partially subducted or whatever. So it gets squeezed, it gets heated. You've got a range of different conditions they can be subject to. So these types of processes will occur on a much larger scale. So if you look at metamorphism around, say, the Cornish granites, you're looking at processes that operate over, you know, kilometre scale. If you're looking at regional metamorphism, you're looking at processes that operate over maybe hundreds of kilometres. And the problem you have is, in both types, is that you start with a whole bunch of different rocks, because rocks are anyway very diverse, and then you subject them to really quite variable conditions. Could be high pressure, low temperature, low pressure, high temperature. And the outcomes will be different in each case. So this is why metamorphic petrology is such a nightmare, because you've got a whole variety of different starting points, you've got a whole variety of different processes, and it shouldn't surprise you to learn that you've got a whole variety of different endpoints. And I've just put 3 pictures of metamorphic rocks up to illustrate that you can get all sorts of quite intense alteration, down to almost complete remelting and recrystallization. And part of the game is trying to understand, if you get something like that, that's clearly not what it started out as, but so how do you work backwards from that to understand its geological origins and history? That's all I will say about metamorphic rocks. Okay, I alluded to this earlier, that rocks are often thermodynamically unstable on the surface of the Earth. And we've got a bunch of processes which we've started to talk about a little bit already, which I'm lumping together and calling weathering and alteration. So you have physical processes and you have chemical processes, and you being chemists, I'm spending a little bit more time on the chemical ones. So we'll look a little bit at dissolution, we'll look at hydrolysis reactions, and we'll look at oxidation and reduction reactions. And these processes are important because clay minerals, which I've just sort of introduced into the discussion, and you've all sort of heard of clay, they're not primary minerals at all. They turn out to be really quite important, but they are secondary minerals. They're produced by all these processes. Okay, so let's think about the physical side of weathering. So all we're doing is, weathering as a whole is transforming minerals into other thermodynamically more stable forms. And weathering reactions will lead to changes in both physical structure and chemical composition. So this is in the high Arctic. You can see some glacial landforms around, so you can see essentially big heaps of gravel that have been scraped up and bulldozed around by ice movement and by water movement. So that those destructive processes are part of physical weathering, purely about changing the physical form. I mentioned the residual stresses around grain boundaries. Well, eventually, if you do freezing and thawing and freezing and thawing, that stress will turn into a microfracture. And then water will go into that microfracture just through capillary action. And then if you freeze it, that water will expand. So you will start to lever the sides of the microfracture apart. It will become less a microfracture and over a long period of time, more like a visible fracture. So what you gradually get is a weakening of the physical structure. And then when you've got some high energy physical process, whether it's ice movement, water movement or air movement, then you will actually physically start to remove little bits of the rock. So, and sometimes, for example, if you have a lot of suspended particulate anyway, whether that's a fast-flowing river with a lot of gritty bits in it, or whether it's a sandstorm, because that is then quite aggressive and abrasive, that will in itself increase the erosion of a rock. And I mean, ice in the UK, a lot of what we see on the Earth's surface is actually a result of glacial history, and glaciers are really quite destructive. So you can easily have a kilometre of ice, so it weighs a lot, and they can move meters to tens of meters in a day. So that's a pretty effective way of scraping up large quantities of rock and crushing it. And we've got various random pictures. So these are some glaciers. You can see them flowing down both sides of this harder rock, and you can see the dark stripes in them. So that's eroded material which is becoming concentrated in particular zones of the glacier. And here is weathered rock. You can see that you've started to develop deep fractures within it. So you've got water's going down there. You'll start actually to get things living down there, plants and a bit of soil, and though soil accumulation. Those sorts of processes will again accelerate weakening and erosion. And you can see here the rounded form of this particular rock. So that's been eroded away, effectively sandblasted away. So I've hinted at this already, but this is trying to put a little bit of order into this discussion as well. When you look at chemical weathering, which we're about to spend a few minutes discussing, there's a spectrum of susceptibility. So for the mafic minerals, so that's the minerals characteristic of low silica rocks, olivine is the most susceptible and biotite the least susceptible. And the observant amongst you will note that we're going from a mineral comprising isolated silica tetrahedra through single chains, through double chains to sheets. So the more connected your silica tetrahedra are in the structure, the more resistant to weathering the mineral is. And over here, on the high silica, the minerals that are characteristic of high silica, felsic minerals, first to go are the feldspars. And that's essentially because you've got some chemistry you can do, because you've got the charge balancing sodium or calcium in there. And potassium feldspar, the alkali feldspars tend to be a little more resistant. Then you've got muscovite, which is a mica, and quartz. So quartz is tough as old boots, which is why sand on a beach is mainly quartz, because it doesn't really do anything. It just gets eroded out and it floats around as little grains of silicon dioxide. So let's look a little bit at the chemical side of weathering now. Now you're used to thinking of dissolution as a process which converts a solid into solvated ions in solution. And that's certainly possible in the natural world. So you can have either complexes of metal ions and counter ions, or you can have colloidal species. Are we clear on what colloids are? Ooh, good, right. Yes, well, nature gives you colloids as well, though they tend to be much less well behaved than the colloids one makes in a lab. But colloids are nevertheless important as vectors for things that stick to them, and we'll see that later on. Now, most of the minerals we encounter, although I've said they're thermodynamically unstable, they're actually still relatively insoluble in water. You know, if you go back to that previous slide, if I take a piece of olivine and I drop it in a glass of water, that will be an incredibly boring experiment. Very little will happen for a very long time. So you don't see, with the exception of the obvious things like halite and sylvine, you don't see very rapid dissolution. And you start to get into all the equilibria that govern these sorts of dissolution processes. So let's take one of the simplest to illustrate the point. So let's just dissolve, I think my battery's going, dissolve a bit of silica quartz in water. That forms silicic acid, which can dissociate to give you protons and the H3SiO4- anion. Now that acid, silicic acid, is a very weak acid, so the first dissociation constant is about 10, which means that unless you're at high pH, almost very unusual in a natural system, then actually this second equilibrium is really not important. And actually what you're talking about is simply the equilibrium between water and solid silica on one side and undissociated silicic acid on the other. And it's actually very simple in these cases then to start to reverse the equilibrium, because all you've got to do is take off some of the water, evaporate it a bit, and it'll move back this way and precipitate silica again. Calcite is a bit more complicated. So we can write this sort of equilibrium. Water plus calcium carbonate in equilibrium with calcium ions, carbonic acid, and a couple of hydroxides. And if you look at this equilibrium, it lies very much on this side. So again, this is why we can make buildings out of marble. Marble is calcium carbonate. Even if it's rained on, and you've got that to happen, the equilibrium is still mostly over here, so your building will not dissolve happily in the first rain shower that comes along. But one of the things that's important is to understand the system you're dealing with. And if this is a realistic description of the calcium carbonate dissolution reaction, then if you increase the concentration of carbonic acid, you would expect the equilibrium to respond by moving back this way and precipitating out calcium carbonate. In other words, the more carbonic acid you have around, the lower the calcium carbonate solubility. But actually, most water is not H2O actually. Most water contains quite a bit of dissolved dissolved CO2. And actually, you're maybe better to formulate the reaction like this. So carbonic acid plus calcium carbonate in equilibrium with calcium in solution and hydrogen carbonate ions. This matters because now what we're saying is if we increase the carbonic acid concentration, we'll push the reaction this way. In other words, higher carbonic acid concentration will lead to higher calcium carbonate solubility. So the key point I want you to take from this is that the way you put your chemical model together matters. We put it together this way, and we predict one effect of higher H2CO3. We put it together this way, we predict precisely the opposite effect. So the way you formulate the system matters because it will influence your interpretation of the results. And similarly with hydrolysis, we can write reactions like this. So this is our olivine, magnesium silicate plus water in equilibrium with all that lot. Or if we're treating water as dilute carbonic acid, we can write a reaction like this. And I don't know why my equilibrium arrows have disappeared. This first reaction is going to suggest that your solution pH ought to go up. But when you start to get to high pHs, then you're going to effectively buffer the system because you're going to start to dissociate silicic acid. And when we come to more realistic phases, so here we've got a sodium-rich feldspar, you can formulate these sorts of reactions. So sodium aluminium silicate plus water plus carbonic acid is in equilibrium with sodium ions in solution, so they've dissolved out. Silicic acid, which wanders off, and we're left with this thing that sits behind, Al4Si4O10OH8, which is the mineral kaolinite, out of which they make chinaware, they use it as coatings on paper and so on. Kaolinite is the first example we've properly met of a thing called a clay mineral, and we'll come back to them later on. I'm going to stop there because we're about to look in detail at the process by which this sort of reaction occurs, and it will take more than the minute and a half I have left. Thank you very much. See you next week.